All right, grade 10. So we are going to just consolidate our learning on electricity. And I know here in the Western Cape, most schools are beginning their tests. Some schools have finished. And using, of course, the remainder of April to get ahead on term 2 work. So there's obviously more time for revision. Okay, but those starting around about next week, 8th of April, and leading all the way up into April. Hopefully this video will benefit you. And the session will benefit you guys. Okay, I do remember doing question 4 earlier in one of the previous sessions, so I'm going to start with question 5 today. Question 5, there is 5.1 to 5.4, all different types of circuits, resistors connected differently. All the resistors in the following diagrams are identical. Each resistor has a resistance. Alright, see it's misspelled there, but it has a resistance of 10 ohms. Calculate the effective resistance of each combination of resistors. So for 5.1, we can obviously start by identifying certain things. Okay, we can identify that all resistors in that circuit, in that part of the circuit, is connected in series. Alright, 5.2, we have a parallel circuit there connected, and it looks like there was supposed to be a other resistor drawn here where we see this 10 ohms. So I'm going to say insert another resistor in series here for another 10 ohm resistor in series here. So we have two resistors connected in parallel and a third resistor in series to this parallel circuit for 5.2. 5.3, two parallel circuits after one another. 5.4, the reverse of 5.2, of course, or the inverse of 5.4, the series resistors connected first and then the parallel resistance. The same also for 3 marks. 5.2, 5.4, also 3 marks, so the same type of working is going to go there. And 5.3 as well, 3 marks as well. Okay, so 3, 6, 9, 10, so about 11 minutes. Okay, to complete this question 5, we just calculating resistance, and then we'll mark through at the end with our solutions. Alright, so for question 2 involved a parallel circuit first, over here, this one, and there was a third one there that seems to be missing for some reason, but don't worry about it, no worries, we're going to keep going with it. So the first thing to do would be to do the parallel resistance formula. Now there are 2 ways, of course, you can do this. The one, of course, saying that R parallel is equal to R1 R2 all over R1 plus R2. So the numerator is saying the resistance of the first resistor times the resistor of the second resistor all over the resistors added together. So in this case, our resistors are all 10 ohms, so 10 times 10, alright, divided by 10 plus 10. Okay, so of course that's 100 divided by 20. Okay, now my brain is fried for some reason, but if we take 100 and we divide it by 20, we're going to get 5 or 5 ohms. Okay, the other way, of course, you can do it is using the second parallel formula, which is 1 over R parallel. So either 1 over RP, or sometimes we write it with just parallel lines. 1 over R1 plus 1 over R2. It does eventually lead to the exact same thing as this. So 1 over 10 plus 1 over 10. Okay, so all we do is we just put that in our calculator. 1 over 10 plus 1 over 10 leads us, of course, to 1 over 5. Okay, and all we do is we invert to take the reciprocal, and therefore our parallel is going to equal 5 ohms too. Okay, most people do prefer using this one, especially when there is 2, right? 2 or more. You can use the first one, but of course, excuse me, ladies, if there is more than 2, this way is most effective. Okay, because this one only works for 2 resistors. Okay, this one is for 2 or more. Okay, but that's not total resistance. Okay, we want a total resistance there in the circuit. So we know that the resistance in parallel was equal to 5 ohms, and there's another 10 ohms still waiting. So the total resistance there is going to equal to 15 ohms for circuit number 2. Okay, the parallel resistance we calculated to be 5 ohms plus the 10 ohms there, 15 ohms. Number 3, we had 2 parallel resistance. Okay, now this one's a little bit easier because we know that both of them is going to equal 5. Okay, so we know that this branch is the same as this branch here because they're all equal to 10. So we know it's going to be 5 plus 5, which is going to equal 10 ohms. Okay, shortcut, we didn't even need to think. And number 4 answers the same as answer in 5.2. Total R is equal to 15 ohms. Well, at least that's how I understood 5.2, because it says 10 ohms there, so there's something missing. So that's how I understood it to be this. Okay, might have interpreted wrong, but for the purposes of just my eye and just looking, that's what I interpreted as. Okay, so obviously the next 2 were a bit simpler because we did most of the work on 1 and 2. Question 6, grade 10s, nice question. 3 identical cells are connected in series to make a battery. The battery is connected to 2 identical 6 ohm resistors, which are in parallel. When the switch S is closed, the ammeter reads the current in one of the excuse me, ladies, I had a sneeze. In one of the parallel branches as 600 milliamps. For 2 marks, 6.1, determine the current through the other parallel branch. So the answer to this question, determine the current through the other parallel branch, is quite simple. Okay, it's the same value. Alright, the ammeter, which is incorrectly drawn as a voltmeter here, unfortunately. Okay, that should be an A and not a V. Voltmeter is right to be across this parallel branch, or connected parallel across this battery, because a voltmeter is connected in parallel and an ammeter is connected in series. Okay, very important. A voltmeter is always connected in parallel, but a ammeter is connected in series. Okay, which it is correctly drawn, just not correctly stated. All right. Now that that's out the way, the current passing through, or the current through the other parallel branch, is also 600 milliamps or 0.6 amps. That's why it was for 2 marks. We didn't have to calculate anything. The marks came from the value and you're using the correct SI unit. So 600 milliamps or 0.6 amps. That was pretty easy. 6.2, now we can see by the mark allocation we have a calculation question which says calculate the potential difference across the battery. So they want the potential difference across the battery. We have now the current and we need to calculate the potential difference. Okay, and we have the resistance as well. So we can calculate the potential difference going across the battery. Okay, and that's 4 marks, so I'll give about 5 minutes. Okay, so let's have a look at that solution. That was 6.2. Okay, and one of the best ways to approach this question is just to have a look at this formula, which is called R is equal to V over I, which wasn't really in the grade 10 syllabus, but sometimes it gets factored in, but it's usually only taught in grade 11, which is a law that exists in circuits, electric circuits, called Ohm's law, and I did mention it in 2 weeks ago, alright, called Ohm's law. Okay, we were told that the resistance, of course, where the current is situated, is 6 ohms. Okay, and we obviously need to find the potential difference, which is unknown, but the current in the circuit is 0.6 amps, 600 milliamps, but we use amperes to measure current, so it's 0.6, and of course we multiply both sides by 0.6. Okay, and then we get an answer. Therefore, the potential difference across the battery is 3.6 volts. All right, 3.6 volts. Okay, so that's the reading that is over here on this voltmeter. The next question, 6.3, the current that's passing through the battery. That's a 2-mark question. That's a very easy question. So the first question was determine. So we already know the current passing through this branch, and we just answered the question, the current flowing through that branch, which is also the same amount of resistance, 600 milliamps flowing through here. So 600 milliamps should also be flowing through here. And if the equation in 6.3 is calculate the current that passes through the battery, which powers the entire circuit, then that is simply I is equal to, which is current, 600 plus 600, of course, which is going to give us 1,200 milliamps, right, which is basically equal in amperes to 1.2 amps, and that's our final answer. Question 9 is the next set of questions. Question 9.1, we're not going to do all of question 9. We're just going to do some of question 9. Question 9, we're just going to rock up all the way up until about 9.5, 9.1 to 9.5. Okay, number 1, explain what is meant by the current is 2 amps. So we explain in that statement by giving a definition of current, of course. 9.2, calculate the charge that passes through the resistor when a steady current of 2 amps is maintained for 2 minutes. Okay, that is our other formula we learned at the beginning with charge, current, and time. 9.3, explain what is meant by potential difference across the resistor 4 ohms. Again, explaining a term. 9.4, calculate the energy transferred by the charge when a steady current of 2 amps is maintained for 2 minutes. Again, that's the formula of voltage or potential difference is equal to work or energy divided by the amount of charge. And 9.5, explain what is meant by resistance in an electric circuit. That's also a definition, and we will get to that in about 15 minutes. Okay, so let's attempt 9.1 all the way through to 9.5, and I'll provide solutions soon as you have grappled with the questions. Alright, so just to remind, 9.1, explain what is meant by the current is 2 amps. Okay, so that is basically asking for the definition of current. Okay, current is, of course, the rate of flow of charge. Okay, but when they say the current is 2 amps, what are they saying? They are saying, according to this formula here, remember, for current, let me just change the layer here quickly. For current, we know we have I is equal to Q divided by delta T. Okay, so obviously the definition in grade 10 for current, and even in grade 11 and 12, current is the rate of flow of charge. Okay, but now they're saying that I, or the current, is equal to 2 amps. Okay, so what they're essentially saying, the whole answer to that question 9.1, the rate of flow of charge is basically 2 coulombs per second. Okay, 2 coulombs per second. If you ever get a statement, the current is so many amps, or the current is 2 amps, 3 amps, 7 amps, 10 amps, they're basically saying the rate of flow of charge is equal to that same number. So if it was 2, 3, 4, 10, whatever, coulombs per second. That was 9.1, and it's all derived from this formula that we see over here in the corner. Okay, I'm going to take away this part here. Okay, for 9.2, however, this was a different question. 9.2 said calculate the charge that passes through the resistor when a steady current of 2 amps is maintained for 2 minutes. Now we definitely use this formula again. I is equal to Q divided by delta T. Okay, so over here, that's the method. Of course, we're told, of course, the current was 2 amps, so we substitute. So right here, I is equal to 2 amps, and delta T was equal to 2 minutes, which is equal to 120 seconds. Okay, remember, because we need to convert minutes to seconds. And they're again asking for calculate the charge that passes through. So Q is our unknown. So we leave Q on top here untouched, and we just convert 120 seconds there, so which is 60 times 2. Okay, 60 seconds in a minute. Okay, multiply both sides by 120. Okay, to balance them out, of course. Therefore, the charge is basically 240 coulombs. All right, that's passing through that point in 2 minutes. Okay, so that one was pretty basic. Move on to 9.3. Okay, 9.3, explain what is meant by the potential difference across the resistor is 4 volts. Okay, again, this is a definition. So basically saying that the energy transferred per unit charge across the ends of the resistor is 4 joules per second. And it comes from this formula, V is equal to W divided by Q. That's the definition essentially. So it's saying that the energy, W, transferred per unit charge, Q, across the ends of the resistor is 4 joules per second. Alright, i.e. 4, let me write i.e. first, i.e. 4 joules per second. Alright, so alternatively to what volts is going to be equal to. Okay, for 9.3. Okay, so let me say that definition again. The energy transferred per unit charge across the ends of the resistor is 4 joules per second, which leads us into obviously the question 9.4, which calculate the energy transferred by the charge when a steady current of 2 amps is maintained for 2 minutes. So again, I is equal to 2 amps, delta T is equal now to 120 seconds, which is 2 minutes, and they want the potential, or no, energy transferred, sorry. They're looking for the energy transferred, which is W. Okay, so now we know the result of these two in terms of what Q is going to equal. Okay, Q is obviously equal to 240 coulombs. Okay, and 40 coulombs. Okay, and they also mentioned that of course the potential difference across the resistor was 4 volts, and calculate the energy transferred by the charge when a steady current of 2 amps is maintained for 2 minutes. So again, the formula V is equal to W divided by Q. V was 4, taken from our previous statement over here. Okay, 4 joules per second, 4 volts. W is unknown. Q was 240, calculated by just taking, because it's the same numbers. Okay, multiplied by both sides. Therefore, W, let me just make the W a little bigger here so doesn't look like we're calculating weight. Okay, W for work or energy transferred is now equal to 960 joules, because work is energy transferred and energy is measured in joules. Okay, 960 joules. Okay, hope you all got that. The final question, 9.5, explain what is meant by resistance in a circuit. This is very easy because we all know what resistance means in terms of everyday life. The resistance is the opposition, all right? It's opposing, all right? Motion or notion, all right? It is the opposition. But with electric circuits, resistance is the opposition to the flow of charge. It's the opposition to the flow of charge. And that's the definition for resistance. Alright, we're just going to switch now to some multiple choice questions quickly. Just to, again, give the brain, not used to just doing one thing at the same time, but still be able to process some information and recall information that we needed to recall. 1.1, the diagram shows a circuit containing 3 bulbs and 3 switches. S1 to S3 is a switch, and bulb 1 to bulb 3 would be a bulb. Bulb 1 and bulb 3 are lit, okay, but bulb 2 is not lit. Which switches switch or switches are closed. Okay, very interesting. Okay, let's think about that answer. So I've just received an answer from a lovely student who's answered with option C, that switch 1 and switch 3 are closed. And that is the correct answer, and also makes a load of sense, because the current must pass through bulb 1 and bulb 3 when those switches are closed. The fact that switch 2 is not lit means that switch 2 is not closed, right? Unfortunately. Okay, so option C it is, only switch 1 and only switch 3 are closed. For this next question, refer to the circuit shown below to answer both questions 1.2 and 1.3. So let's answer 1.2 first. The ammeter reads 2.0 amps, which is 2 amps, and the voltmeter reads 12 volts. Right, the voltmeter reads 12 volts. The question is, how much charge passes through the resistor in 10 seconds? So I got an answer from another student as well. Selected answer or option B. So let's take a answer and let's apply with a formula. We know that current is equal to Q divided by delta T. And they told us that the current was 2 amps, so we're filling 2 or 2.0, it's the same thing, is equal to Q, because they're asking how much charge passes through that point in 10 seconds. So delta T is equal to 10. Multiply both sides by 10, and therefore Q is equal to 20 coulombs, which was option B. Okay, so option B for 1.2. We have one more question to answer here with regards to this circuit, which is 1.3. 1.3's question is, how much energy is transferred by the resistor in 10 seconds? So this is something I'll jump on. Okay, now remember the formula at the top there was V is equal to W divided by Q. So there's no time. So time's not going to play a factor here necessarily. They just mentioned that it was in 10 seconds. So we used the 10 seconds already. So we need, of course, the energy transferred. And they told us the voltage, which was 12. Voltmeter read 12. The energy is what we're trying to find out. But the charge we know is 20. Divide or times both sides by 20. Therefore, the potential, the energy transferred rather, is equal to 20 times by 12, and that is 240 joules. So you can see this is quite, depending on the nature of the question, doesn't really matter, but once we know the theory and we know how the formulas work and understand them, we are able to approach these questions and answer them with ease. Okay, we're going to move to question 3. Nice question. They follow on from one another, typical type of exam or test question. Question 3, circuit 1 and circuit 2 consist of a 12-volt battery connected to a 160 ohm resistor and a light bulb with a resistance of 240 ohms. So they both, circuit 1 and 2, have the same components, same values. Okay, only difference, 3.1 says describe the arrangement of the resistor and light bulb in circuit 1. So the arrangement is, of course, there's only two types of circuits we get, series or parallel. You got to tell me how it's arranged. Okay. Let me see. Yes, that's 3.1. 3.2, calculate the equivalent resistance of circuit 1. Okay. 3.3, calculate the current through the light bulb in circuit 1. So we're going to do everything for circuit 1, and then we're going to move on to circuit 2 for the next 3 questions. So 3.1 through to 3.3, let's go. So now 3.1, describe the arrangement of the resistor and light bulb in circuit 1. Okay, so we can clearly see what circuit 1 is, a parallel resistor, or parallel circuit rather. The two components of the circuit are connected in parallel. Okay, both of them have a resistance. Okay, so they're both giving ohm readings. So the voltmeter is parallel to the 160 ohm resistor, which is also in parallel to the 240 ohm resistor or resistance of the light bulb. So the arrangement of the resistor and the light bulb in circuit 1 is they are in parallel, right? They are both in parallel. They're in parallel with each other. Okay, that was pretty basic. That was pretty easy. Okay, 3.2 though asks calculate the effective resistance, or sorry, not the effective, the equivalent resistance of circuit 1. We shall attempt to do that. Okay, so equivalent resistance, so 1 over R parallel is equal to 1 over R1 plus 1 over R2. You're welcome to also use the other formula. It would have also worked out. We'll do both. Okay, in fact, we'll just undo that. Right, and then we'll go R parallel is equal to R1, R2 divided by R1 plus R2, but we'll do this one first. So 1 over R parallel is equal to 1 over 160 plus 1 over 240, and that would have given us first, before we invert it, 1 over 160 plus 1 over 240, 1 over 96. Okay, let's check that I've done this correctly. Yes, 1 over 96. Okay, this is what my calculator's giving me. 1 over 160 plus 1 over 240. Okay, cool. And if you invert that, take this away here quickly, and therefore if you invert it, R parallel should equal to 96 ohms. So let's just check this one quickly, the second method. 160 multiplied by 240, all divided by 160 plus 240. Okay, and therefore R parallel, they should give us the same answer. 160 times 240 over 160 plus 240. Yes, they do, which is 96 ohms. Right, excelente, as they would say in Spanish. Okay, that was that one. And 3.3 said calculate the current that's going through the light bulb in circuit 1. Okay, now it's always important to check your formula sheet here, as they gave us at the beginning of this sheet. Okay, we had a formula sheet up top here somewhere. Okay, so we make use of the R equals to V over I formula now for 3.3. So 3.3, we have R is equal to V divided by I. Okay, and that would be equal to, of course, the resistance, which we worked out parallel, because the question again was calculate the current through the light bulb in circuit 1. So the resistance there was 96, which is the equivalent resistance across these two branches. Okay, so it's 96 is equal to the voltage in the circuit, which is 12, divided by I. Okay, because the current will be the same for across the branch, because it splits up in two and then links up again. So we end up with I equaling to 12 divided by 96. And we pop that in the calculator, and therefore the current that's going through the light bulb in circuit 1, 12 divided by 96 on my calculator, is about 0, I'm going to round off to 3 decimal places, 0,125 amps, or if you rounded it off to 2, 0,13 amps as your final answer there for question 3.3. Question 3.4, calculate the equivalent resistance of circuit 2. And 3.5, calculate the current through the light bulb in circuit 2, and then 3.6, the potential difference across the light bulb in circuit 2. Circuit 2 we can see is a series circuit. Okay, so let's go ahead and calculate the equivalent resistance of circuit 2, and then let's mark. So for the solutions of 3.4, the equivalent resistance of circuit 2, so this is a series circuit, so it's simple. R is equal, or you can say REQ for equivalent resistance, was just R1 plus R2. In this case it's 160 plus 240, which should equal 400. Drop my calculator if you're wondering what that sound was. 400 ohms. Okay, so that's easy to marks. Okay, for the value and the SI unit. 3.5. The question I think was to calculate the current passing through the light bulb in circuit 2. So here we're going to use again R is equal to V divided by I. So the way to answer these questions is just to see what you have and what you need to work with to get something that is unknown. In this case, we worked out the resistance in the circuit to be 400, right? Which is the total resistance of the entire circuit. Okay. The voltage was 12 because we're using the entire circuit's potential difference, and we're using the entire circuit's resistance. Okay, so if we work with entire, we must use the other one also with entire. Okay, we can't just put the light bulb's resistance then, because then we have to calculate what's the potential difference across the light bulb itself. And of course we have I at the bottom, which will end up just being 12 divided by 400, and therefore the current in the circuit which will pass through the light bulb is 0, I just want to verify this number quickly. 12 divided by 400, it is 0.03 amps. So what that means is that current will run through the light bulb, through the resistance, the resistor, etc., etc. And then 3.6, calculate the current. Sorry, 3.6, calculate the potential difference across the light bulb in circuit 2. So 3.6 we can do over here, which is what I mentioned in 3.5. We still use the same formula, R is equal to V divided by I. But now we take the resistance of the light bulb, because we're trying to find the potential difference of the light bulb only across the light bulb. Okay, the current that's in the circuit, of course, is 0.03. That's flowing through both components, okay, because it's in the circuit. Okay, and does pass through this light bulb, and therefore we know it's just 0.03 multiplied by 240, and therefore the voltage is equal to, across light bulb 2, or just across the light bulb, sorry, in circuit 2, is equal to 7.2 volts. So V is equal to 7.2 V. Okay, let me just make my 7 look decent, because it's going to bother me. Okay, there we go, 7.2. Okay, and I think that's all where we are going to end it for today. Thank you so much, grade 10s, for joining my session today on electric circuits. This is the last one. We've put this topic to bed. Please stay tuned for the next video where we'll have a look at the next topic.